Welcome to This Explainer. Today, we're diving into a genuinely fascinating GitHub repository. It's a runnable, minimal port of Sakana's Digital Red Queen concept. And it tackles what is arguably one of the most frustrating challenges in AI right now. I'm talking about how to build AI system prompts that actually survive the absolute chaos of real-world changes. If you've spent any time building agents, you know exactly how fragile they can be. So let's jump right into how concepts from evolutionary biology are solving software brittleness. So let's talk about this universal developer pain point. We have absolutely all been there, right? You craft this beautiful system prompt, it works perfectly on Tuesday against your test suite. It's flawless. But then Friday rolls around, a database schema shifts just a tiny bit, or the real-world workload throws a totally weird edge case at it, and boom, your agent breaks entirely. Why? Because it didn't actually learn to solve the underlying problem. It just memorized how to pass a highly specific static test.
And that distinction right there is the core of the problem. When you optimize against a single, fixed benchmark, what the repository calls a single round baseline, you end up with brittle specialists. They're totally over-indexed on today's problem. What we actually need are robust generalists, and we get those through coevolution, which is a continuous, adversarial, back-and-forth process.
Here is our quick roadmap for today's explainer. We'll start with the brittle prompt problem, move into the Red Queen solution, look at co-evolving AI populations, check out the SQL and codomains, talk about measuring true generality, and finally wrap up with running it safely. First up, let's quantify the brittle prompt problem. The data on this is actually wild. The repository notes that if you optimize a prompt against a fixed benchmark, the resulting specialist prompts only beat about 28% of held-out on-scene cases. That means a massive 72% of the time, when faced with a slightly new query or schema, they just fail. They're completely overfitted. You aren't building a robust AI agent at that point, you're essentially building a glass cannon. It looks impressive, but it shatters the second it hits something unexpected.
Moving into our second section, the Red Queen solution.
Okay, so how do we fix this? We look to nature. Specifically, the Red Queen effect. If you remember Alice in Wonderland, the Red Queen famously tells Alice that it takes all the running you can do to keep in the same place. In the context of this repository, it means that to create a genuinely robust agent, your prompt has to evolve against a constantly growing history of adversarial challenges. Not just a static test, but a living, breathing opponent. If the adversary gets smarter, well, the prompt has to get smarter just to survive.
Section 3, Co-evolving AI populations. Let's get into the mechanics. To actually create this evolutionary pressure, the system splits into two distinct warring populations. On one side, you have the generators. They're tasked with either creating completely novel system prompts, kept strictly under 90 words, or mutating existing ones. And they aren't just swapping out synonyms. They are instructed to change the fundamental strategy. Then, on the other side, you have the adversary. Its entire reason for existing is to spin up brand new, devilishly hard cases designed specifically to break the current champion prompt.
Under the hood, this whole arms race runs on two highly efficient loops. You've got the outer Red Queen loop, which focuses on stacking up those new adversaries and growing the historical gauntlet the prompt has to run. And then there's the inner loop, which uses an algorithm called Map Elites. This inner loop seeds a quality diversity archive, mutates the prompts, and evaluates them all concurrently using a thread pool executor. That parallel processing is super important because evaluating all these prompts means a lot of LLM calls, so it's heavily I/O bound. Now, you might be wondering, why use Map Elites specifically for that inner loop? Well, it absolutely forces diversity. Map Elites tracks behavioral traits, things like how long the prompt is or its overall level of reasoningness, and it organizes them into specific behavioral cells. An offspring prompt can only replace an incumbent if it beats it inside that specific cell. The repository makes a great point here. Without preserving this kind of forced diversity, everything just collapses into a single generic strategy and performance totally tanks in later rounds. Diversity is literally your shield against unknown future adversaries. Let's look at Section 4, our domains, SQL, and code. So how does this actually look in practice? The repo provides two practical domains right out of the box. First, for the text-to-SQL domain, the genome, the thing you're evolving, is a SQL system prompt. The challenge it faces is a schema, a question, and a gold standard SQL query. Its fitness is judged objectively.
Does the predicted SQL's actual result set match the gold standard in a throwaway DuckDB? On the flip side, the code improvement domain evolves a bug-fixing prompt. It gets a buggy Python file, and it only survives if the AI's patch makes a PyTest command exit with a 0, meaning it actually fixed the bug. A couple of really smart details to point out here. For SQL, the system compares the final result sets, not the raw query strings. This is huge, because it correctly rewards semantically equivalent queries. If your agent writes the query in a weird way but gets the exact same correct answer, it passes. For code, PyTest acts as the ultimate runtime judge. Also, if you just want to test your local plumbing without burning through paid API tokens, there's a super handy mock mode that intentionally returns a 0 fitness score. Plus, to maximize your speed, you can split the tasks, use a heavy-duty instruct model to evolve the prompts, and a fast, cheap coder model to do the actual working and testing.
Section 5. Measuring true generality. So, how do we know if any of this is actually working? The repository is crystal clear about this. The headline metric is absolutely not how well the prompt beats the current adversary in the current round. That's just a local victory. The real metric is the generality curve. That's the fraction of success a champion prompt achieves against a completely held out, totally unseen challenge set over time. If your prompt can solve problems it has never ever been trained against, then you have achieved true generalization.
By tracking that generality curve, a rising line mathematically proves that the red queen effect is real. You aren't just overfitting to whatever trick the adversary pulled last round. Alongside that, you can track the QD score, that's the quality diversity metric, to monitor the overall health of your inner loop. And crucially, if you run multiple independent seeds, you want to see phenotype convergence. Basically, if the variance across different runs decreases over time, it tells you your AI is naturally homing in on a genuinely robust general strategy, no matter where it started.
Finally, Section 6, running it safely. Look, anytime a system executes AI-generated code and SQL, we absolutely have to talk about safety. It is critical to lock down your local environment, and this repo handles it beautifully. For the SQL side, it completely isolates DuckDB by disabling external access. That stops a maliciously crafted query from, say, reading your AWS credentials or password files. For Python, every single evaluation runs inside an ephemeral, temporary directory sandbox. The verification command itself is hard-coded. It's never pulled from the model's output, and hard timeouts are enforced, so an AI-generated endless loop won't just sit there and freeze up your machine.
So, what does this all mean for us? Well, by replacing those static, brittle benchmarks with a constantly evolving digital red queen, you can build AI tools that actually adapt instead of breaking. You forge agents that are hardened by an endless history of adversaries, ready for whatever weird schema changes or production edge cases the real world throws at them. So, the question I want to leave you with today is this. How will you apply this evolutionary engine to your own stack and evolve your next AI agent to truly survive the real world? Thanks for hanging out with me for this explainer, and happy building.